So now in this video, we're just going to take a quick look at the capacitor component. We're going to focus on a couple higher value capacitors. They go a ton lower than this. And this is a 1000 microfarad, and that's a 100 microfarad capacitor. These have to be inserted in the right direction. So that side has to be, the side with the dash has to be more negative than the side without the dash. And the side that can be more positive has a longer lead. The side that needs to be more negative has a shorter lead, as long as you haven't trimmed them. And a lot of capacitors, especially lower values, less than 1 microfarad capacitors, will probably not be polarized. You can probably put them in either direction. So if you don't see a marking that indicates polarity, you can feel pretty safe, especially if it's a lower value capacitor, that it is not polarized. So to begin with, we are going to first make sure this is discharged. And I saw a shock, so it was not discharged. There was a charge. I went negative rail to discharge it. Power supply's on. I'll turn that off too. But we went negative to negative rail. We got a direct connection, and we saw a little spark. So it doesn't really hurt anything. It may have vaporized some metal within there. But in any case, we want to make sure this side is a little more negative to the more negative side of the circuit. And I'm going to go down here because one of these dots up here is not letting stuff get plugged into it. So I want to avoid that if I can help it. So 1000 microfarad, we're going to use a couple of LEDs. This one we're going to have light up while the capacitor is charging. So it will be gaining current from the positive side of the power supply that way to charge up. And then negative over here because it's to the negative rail. So long lead the anode, we're going to go up 1 row. And in fact, let's move this over because we're going to be putting some other stuff near these components. So move it over 1 and come over here. So long lead the anode up 1 row. We're going to take another LED, wire it the opposite way. So the short lead, the cathode, is going to go up 1 row, long lead the anode down here. And that's because when we discharge the capacitor, this side will be more positive. It'll come to the anode, go through the LED, through a resistor, back to the negative rail over there while it discharges. And as I just said, we're going to take a resistor, and the one I'm looking at is 100 ohm. We're going to look at a couple value of resistors here. This one's 1000 ohms. So we're going to put that there. And then to charge and discharge it, we're just going to take a green jumper. And it's just hanging loose now. We can go from one rail to the other. And the power supply is off. We will turn the power supply on. We go to the positive rail. You can see one of the LEDs lights up, but as the capacitor charges, the LED gets more dim. As the LED is getting dim, the capacitor is not charging as fast because there's less current going into it. But there's a rapid voltage change at first, and we know that because there's more current. The LED is brighter. But as the voltage equals out, it pushes. The charge is less. You get less current and less voltage change at the same time. That's the main takeaway. So this is with a 1 kilo ohm resistor. It's probably taken about 5 seconds to go from that first bright flash of light till it fades to nothing for the most part. So that is with the 1 kilo ohm resistor. Let's take a 100 ohm resistor and we'll do another visual check of this circuit here. So 100 ohm resistor now, 1/10 of the resistance. What that means is it will take about 1/10 of the time for the bright flash to turn into practically no light at all. So these kind of light up a little bit with a tiny bit of current. You can see it has a slight glow, but really very little current is flowing right now. Other LEDs, you probably won't even see a light glow by that point. But let's do the same thing with the original flash. See how bright it is. So this will discharge, and there you can see the it's just a very, very low glow right there. Few charges moving, but practically nothing. But these are really sensitive LEDs. They produce a little bit of light, even with hardly any current. So that is with the 100 ohm resistor. Let us go back to the 1 kilo ohm. Take one more look at the charge and discharge. So now it's charged, and now it's discharged. You can see that slow fade. So I just kind of wanted to get a look at that slow fade again, because we're going to yank this capacitor, that's to the negative rail, and replace it with the 100 microfarad capacitor. So a tenth of the capacitance. Again, it's a good idea to make sure it's discharged, and it will be set to discharge even more, but that instantly discharges it because there's no resistance. So make sure we get it to the negative rail there, and we got it plugged in. Now we're going to charge it. We saw it took about 5 seconds before to give a bright flash to almost nothing, and now it's probably about half of a second, at least for the same light level that we had for 5 seconds before. So these aren't precision components. They may kind of drift from their rated value, but for the most part, this one has about 10 times as much energy storage capability as that one per volt. So now we got those two out of the way. Let's yank this one and put the 1000 microfarad back and look at it with the oscilloscope. So again, we're going to make sure it's discharged. This circuit's not a big concern, and if you think there might be a high voltage charge, especially on a capacitor, looks like it, yeah, it was discharged, so it charged through here. If you think there's a high voltage stored on there, you could discharge it through a resistor. It just takes a little more time, but you don't get a spark or anything. So let's turn the oscilloscope on. This one's a pretty simple one. I already have it set up for 0 volts at the bottom. We do need to clip the probes to the board though. So this cable here comes to alligator clips. I have alligator clips that I crimped to the wire there. And this one we can put to either negative rail, doesn't matter. It's a direct electrical connection. And we will take this one and go to where the LEDs, all of that connects. That's one node. So we'll go there and we'll see we got a rise on voltage there. So this is a 5 volt power supply. 1, 2, 3, 4, 5 squares up is 5 volts. We're down about 1.5 because these LEDs block about 1.5 volts. So that's set to charge. Try to make sure. There we go. You can see the jumper there. Now when we discharge it, you see the voltage go down, and it's probably going to take about 5 seconds in that range to go from, there we go, to go from 3.5 volts to 1.5 volts. So we got the one there, and we got about 2/3 of the change there. And then 2 seconds, 3 seconds, 4 seconds, 5 seconds. That's about where it bottoms out, right there. So it's a lot more rapid at first. It's going to be about 2/3 of the change, but per time constant. So with a 1000 ohm resistor and a 1000 microfarad capacitor, which is 1/1000th of a farad, but you multiply those two numbers together, 1000 by 1/1000th, and you get 1. Pretty straightforward. So the LEDs are limiting the curve, as I said. So ultimately the time is going to be the same because they block a certain amount of voltage. They give less of a voltage difference, so there's a little less current, but there's less voltage change as well. So yeah, we can leave that there because that goes to the capacitor. But now we got to move the resistor down 1 row because we removed the LEDs. So there you can see it discharged a little bit more from where it was. Now let's charge it. Now it will go up 5 squares. And again, it's taken about a second to get to about 2/3 of the way. There you can see that's a little more than 3 volts probably, about there. And then less than a volt difference within the next square. And it actually looks like it went up more than a volt. About a volt anyways. But it slows down. And ultimately it takes about 5 of these to get to the final voltage. So again, a little bit of current is still flowing by this point, and because less and less current goes as there's less voltage difference, but the line smooths out pretty much evenly by that point. So about 5 seconds with this resistor and this capacitor. So let's yank out the 1 kilo ohm resistor and look at the same curve with a 100 ohm resistor. And so this is 1/10 the resistance. So it's already charged. Let's discharge it. and you're going to see that curve go probably 10 times as fast. We're using the same capacitor but a lower value resistor. So let's yank that one out, put the 1 kilo ohm back again, and again we have that slow curve there because it's the 1000 microfarad capacitor and 1000 ohm resistor. We'll yank this one out and get the capacitor that is 1/10 the voltage. So this is set to discharge. I will make sure this is discharged before putting it to the circuit. Make sure we got it the right polarity. So now let's charge it. So again, this is the 1 kilo ohm resistor still. Now you see basically the same curve when we had the 100 ohm resistor and the 1000 microfarad capacitor. So this is the 1000 ohm resistor and 100 microfarad capacitor, and so we could either use this resistor and that capacitor to get that time and change of voltage, or we could use the 1000 microfarad and the 100 ohm resistor. So it's a balance between the two of them. The larger value components you use, the slower the voltage change during the charge, and the lower value ones that you use, so that one and that one, would go a whole lot faster. And so you balance them out, usually based on whichever ones you have. If you have a wide variety of resistors to choose from, usually you use a convenient capacitor, and you go from there. I have a kit full of capacitors right here, and I have these values here, so I can go a whole lot lower. That is no problem at all, and that's just this kit. And the 100 ohm or the 100 microfarad capacitor you see here I got from a different kit, but this goes all the way down to I think 4.7 picofarads. So yep, 4.7 picofarads. So it takes 1470 nanofarads to get that much. This is about, I think, a billionth or a millionth less than the size of that one. So a whole lot smaller. But in any case, we use these large values because you can see the LEDs light up and whatnot. So that's really it. That's the all you really need to know about capacitors for the most part. There's smoothing capacitors, which just kind of hold the voltage. So they just got to provide a little charge. You saw we had the LED bright for a little bit. If there's just a real rapid voltage change across that LED, but we had the capacitor here, it would keep it lit, and you might not even notice it dim at all. So that's smoothing capacitor. This is RC time constant. This is almost as common as the smoothing. You see smoothing capacitors all the time. They're not doing anything, just keeping rapid changes from affecting sensitive components. And other capacitors, they are actually looking at the time it takes for them to charge and discharge, or they're allowing brief changes in current and voltage to go through the capacitor, because the circuit was passing current for a brief period of time, but then it slowed down and stopped. And so if you don't want something to continuously flow current forever, you might just charge a capacitor with it, and then once the capacitor is charged, it won't let current go through it anymore. So in any case, this is really about it for the basics for capacitors. You just learn different ways to take advantage of this. And as I said before, lower value capacitors especially are not polarized. Doesn't matter which direction you put them in, you can charge it one way and then charge it the other way. Perfectly fine. So hope you enjoyed the video. Thanks for watching. I'll see you in the next one.